Hi everyone, so today we're going to go over parametric models. Now, the entire idea of parametric models is that they follow this functional form. So there's a fixed form that they have to follow, which is the entire meaning behind parametric. Now, we're going to go over a few different parameter estimation techniques. So first is fixed variable. So this is when you set the first moment equal to the sample mean. So now the first moment, if it's gamma with fixed alpha, binomial fixed m, negative binomial fixed r, which is the same as geometric r equals 1, you set that equal to the sample mean and then you solve for whatever the parameter you're trying to estimate. That is one way to get like an exact estimate of that parameter. So, for example, if we are referring to a binomial, right, we know it's the expected value of is NP, right? Right, which equals X bar or the average, right? Now, if we're looking for parameter P, well, that is going to equal X bar over N. So the average of all the X's, right, over N. Same thing for all these other distributions. If you set the first moment, set the expectation of x equal to the sample mean, and then solve for whatever parameter you're trying to estimate, you can get the parameter estimation. Now, if you can't get it exactly, then that is when we resort to Fisher information, which is the negative expected value of x, d squared d theta squared, natural log of likelihood of theta, or the parameter. Now, how do we remember this? You can think of we're taking the second derivative with respect to the parameter, so that is the inside. Taking the second derivative with respect to the parameter, right, of the natural log of the likelihood function. So inside, we're taking the second derivative with respect to the parameter. On the outside, it's with respect to x. So that is what we call Fisher information. The variance of that, the variance of the parameter, is the inverse of the Fisher information. So that is how we can approximate variance of a parameter. When it is fixed, when we have gamma with fixed alpha and these distributions here, we can get the variance of the parameter exactly, right, by doing manipulations. Now for NIID, right, N independently and identically distributed, Fisher information is equal to the negative expected value of x of the derivative with respect to theta, right, second derivative with respect to theta, natural log of the actual function, right, that expected value times n. So because it's n identically distributed and independent, you can actually just take the expected value with respect to x and then multiply that by n, which represents the sample size. If it is two parameter, we have a matrix and we introduce partial derivatives here as well. So it's the partial derivative of alpha theta, and then the second derivative of alpha, second derivative theta. One of the properties of MLEs is that the function, the maximum likelihood of a function of the MLE is the MLE substituted in within to that function. So what does this mean? This means that the MLE of x squared, right, is equal to the MLE of x squared. Right? So that's an important property. This is what we call delta approximation, which is that the variance of the function of the parameter is equal to the variance of the parameter itself times the derivative of the function squared. And typically when this is a constant, so for example 9 theta, you can actually just take the constant out. It's 81 variance of theta, which is the same. You're doing the same thing as a delta approximation, just the only thing is it's a constant, so you're able to factor out the constant. And this applies to the two-parameter case as well through this formula here. Now, when we do maximum likelihood estimation, when we're trying to figure out what is the optimal value or the most likely value of this parameter, we can do 90% normal confidence interval, we can do symmetric, we can also do linear. And this is how we can get that. Right? Theta hat is the MLE plus or minus that z value, square root of the variance and the approximated variance of that parameter. Chi-squared distribution. So MLE, so the entire purpose of MLE is we have some known data points, right? We have some known data points, and we want to see what is the maximum likelihood estimate of this parameter from these set of data points. We have some fixed parameter, right? That is a fixed parameter of a population. We have some sample data points of a sample. We want to estimate what that population parameter is from that sample. That is the entire concept of maximum likelihood of estimation. What is the highest likelihood, right, that this parameter is such a value, and that is the value. Chi-squared test is a way to understand and quantify model fit. So the test statistic is the summation of expected minus observed squared over expected, where observed is your observed counts, right? If you have different groups, group 1 to group 3, your observed counts for these groups, and then your expected counts are depending upon what your distribution or your alternate distribution is. Okay, so if your alternate distribution, if you're trying to see, does this come from an exponential, right? Does this come from an exponential? You're going to calculate what is the expected number of values that are supposed to be in group 1, group 2, or group 3. Right, so that is the expectation. We take the difference of that, square it over the expected, right? And then you take the sum of that, that is your test statistic. Likelihood ratio test is another way to assess model fit. Does these points, do these points come from distribution A? Do these points come from distribution B? Right, so that's your null and alternate. Test statistic for this is 2 times the likelihood function evaluated at theta 1 minus likelihood function evaluated at theta 2, which follows a chi-square distribution of that test statistic with the degrees of freedom. Right. And again, likelihood function is given this distribution. What is the likelihood that we see this sample or these data points? Or given this parameter, that is the likelihood function. What is the likelihood, given this distribution, we see this data, that we observe this data? Okay, so that's going to give you an idea of what's the probability that the data actually comes from this distribution. Right, and you take the difference of that, that is your test statistic between the difference of the null and the alternate, the fact that it comes from distribution A or could come from distribution B. Difference between those two likelihood functions is your test, times 2 is your test statistic. You can also compare models with different number of parameters. So and why we want to do this, why we have such things as SBC, BIC, AIC, is because We want to mitigate just having a bunch of parameters, right? We don't want, right? More parameters there are, that doesn't necessarily mean a better model, right? We want to also have a penalty for more complex models. And so that is why we're able to have these different metrics, SBC, BIC, AIC, right? Penalizes the model for having more parameters, right? And you can see the formulas there. DX plot and PP plot are also a way to measure empirical versus fitted distributions, right? So DX plot we know is the empirical minus the CDF, right? Minus the fitted CDF. And again, there will be peaks and valleys. Peaks and valleys refer to the actual empirical because it could be less than or equal to, or it could be less than. And so that's why you're going to see certain jumps in the DX plot. PP plot is a plot of the empirical CDF on the x-axis versus the fitted CDF. And you're going to have typically, how do you know if this is a good fit? Well, you have the diagonal line, which represents on this diagonal line, right? What do points on these diagonal lines represent? These represent when the empirical CDF is the exact same as the fitted CDF. And that means our model is a good fit, right? That means our model is a good fit, right? When the proportion of values less than a certain amount, right, by our fitted CDF is the same as our empirical CDF as what our observed data points are, that is a good fit, right? That is a good fit. So we want to compare how does our empirical versus fitted CDF compare to that diagonal line, right? How does it compare to a perfect model or a perfect fit where empirical equals the fitted exactly, right? So how does it differ or vary from that exactness? Well, if it is below the line, and if it is on the left side. So what does that mean? If it is below the line, if it's on the left side, right? Below the line, on the left side, this means that, right, our empirical is greater than our fitted CDF, right? And if our empirical is greater than the fitted CDF, right, that means we have a lighter left tail, fitted lighter left tail, right? Fitted lighter left tail because our fitted CDF is like this, right? Right, it has a lighter tail, and our empirical CDF is slightly higher, right? So our fitted CDF has a lighter tail. The right side, we have opposite case, right side where empirical CDF is less than the fitted CDF. Right? There we have a lighter right tail on the fitted side, fitted CDF. Right? So based upon how it compares to the diagonal line, based upon how it compares to the notion of perfection, which is where the empirical CDF equals the fitted CDF, you can tell if your fitted CDF has a lighter tail, has a lighter left tail, right tail. So these are some ways to model how good your data follows this certain distribution. You can do hypothesis tests. And one of the common questions is chi-squared test. And one of the Excel formulas is chi-esc.dist.rt, which will give you the p-value or the area on the right tail, which is the area of the p-value, right? So that is and then you compare that against your like threshold, your significance threshold, if it's like 0.1 or 0.05 to determine if you reject or fail to reject the null. And a couple of other notes is when you're calculating likelihood function, you also want to be very careful with calculating likelihood function. And whenever you're doing approximation for variances, sometimes you might need the approximation of, you might need the MLE, And so for that, you would have to obviously go through the likelihood function, take the natural log, derivative, set it equal to zero, all that stuff. Right? So to calculate the approximation of variance, you might also have to do that. So that's something you should be prepared to do. But that's a high level overview of parametric models. And I'll see you in the next video.